Hi all, here Professor Ravi Kumar. I welcome you all to the next lecture where today I am going to teach you the concept of entropy. Prior to this lecture, we have covered the second law of thermodynamics where the two parallel statements of second law of thermodynamics were discussed, and corresponding applications also we have seen applications in heat engine, heat pump. Then we have discussed about the Carnot cycle, and parallelly, we have covered the Carnot theorem and corollaries of Carnot theorem, and we end up with the last topic of second law, that is Clausius inequality. Basically, here also we will be starting our discussion with Clausius theorem. So Clausius inequality says that algebraic summation of dq by t should be less than equal to 0. Alright, that is the one thing. By using that equation, we can find out the feasibility of a particular process, or feasibility of a cycle, or feasibility of a device. Similarly, here is Clausius theorem. Basically, for a reversible cycle, particularly or reversible devices, cyclic integration of dq by t should be exactly equal to 0. That is the one thing to be satisfied. Then only you can relate. So today we will see the entropy, like the outcome of the first law of thermodynamics was the internal energy, where internal energy was got defined, and today this is the outcome of the second law of thermodynamics, which is nothing but entropy. So entropy will basically tell about the direction of heat transfer. It will talk about how actually changes are happening in the system. So let's start with the discussion with the presentation. I am going to start my presentation now. So first thing, what is basically entropy? It is a measure of extent of randomness or disorder of a system. So the more disorderized a system, disorganized the system, the higher the entropy. So we'll take an example, right? It is a closed system and we are supplying heat to it. So system will have any sort of working fluid, and working fluid have a number of particles. So when we are supplying the heat, due to supplying of heat, whatever molecules will get excited, and because of that there will be frequent collision or compression of molecules, and randomness in the system will increase. So when randomness increases, due to that properties of system will change. So property change may be either pressure or temperature. So if I assume like that all boundaries are fully insulated, in that case what will happen, the temperature generation which has taken place in the closed system will get stored. So as we know, the heat and work are not the property of system, we cannot store them, so they will be definitely stored in some other form of energy, so that whatever heat has been generated or the temperature has been generated as a result of heat interaction to the system boundary will get stored in a closed system, that is called internal energy. But as we are dealing with the open system, in open system we cannot accumulate anything. So whatever certain mass of certain mass of fluid will enter and it leaves the system. So there is no accumulation, right? And as a result there will be some energy interactions will be happening. So here basically we will talking about the directions and how to measure those changes happening between point and 1 to that will be given by the entropy. So it is also a measure of extent of irreversibility. Whenever there is irreversibility, there will be losses, right? Loss of energy. So this entropy also measures the extent of irreversibility associated with a process. So irreversibility basically will happen only in the process. So when we are talking about system will have randomness or disorder within the system. So it is a quantitative measure of degradation of energy during energy conversion, right? So these are the 3 points, right, regarding the entropy. So it talks about the extent of randomness, disorder to a system. It talks about the extent of irreversibility associated with a process. It is a measure of quantitative measure of degradation of energy. Whenever there is irreversibility will lead to the loss of energy. All right. So it can be defined as right. It is denoted by the capital S. It is a property of system basically. So as per the Clausius theorem, ds is directly proportional to the dq by t reversible. Only for reversible processes we can define entropy in such a way. So when we integrate that, this is a property of system. So it can be written as S2 minus S1, that is integration of dq by t reversible. So change of entropy can be defined based on the reversible process only. So what are the characteristics of entropy? How will you realize that? So one thing, it increases when heat is getting supplied, irrespective of the fact whether temperature changes or not. So it basically depends on the quantity of heat that you are supplying. So the moment you supply the heat, there will be change in entropy, right? So Even though when we are supplying heat, we are not bothering about whether temperature of system is increasing or not. So we are not bothering about that. So basically, entirely depends on the heat supplied or heat rejected from the system. One thing. So it decreases when it is getting removed, irrespective of the fact whether temperature is changing or not. Right. This is very important point that you need to keep in mind. So it remains unchanged in all adiabatic frictional less processes. If it's adiabatic, no heat involved, so no heat involved, so change in entropy is zero, right? Keep in mind. So it increases if temperature of heat is lowered without work being done, as in throttling. So in throttling, what happens? It will be all of a sudden process. So all of a sudden your system will undergo in a sudden expansion. So in that case, definitely entropy of system will increase. All of a sudden, it is getting lowered, right? And there is no work involved in throttling. In that case, entropy will increase because it's a very fast process, and fast process will involve what do we say, irreversibility. So because irreversibility, entropy will increase. So these are certain characteristics of the entropy. Just you keep in mind when we are dealing with the practical application of entropy. So what is the Clausius theorem? As I mentioned, Clausius theorem, as per Clausius theorem, cyclic integration of dq by t should be greater than equal to 0, right? So greater than 0 will be in the case of irreversible process, or if it is equal to exactly 0 in the case of reversible process. So it states that cyclic integration of dq by t for a reversible cycle is equal to 0. So this is a very simple statement given by the Clausius theorem. So let's now we are going to prove that entropy is a property system, because already we have talked about the entropy is a property of system. So how basically it is the property of system that we are going to define. So we will be defining in a similar way. We need to find out two cycles, because entropy that what is the Clausius theorem is applied to a reversible cycle. So we need to assume two cycles, right? So these are drawn here. So one cycle is it is going from point 1 to point 2 via path L and returning via path M, right here via path M, right? 2 to 1 it is coming by path M. This is one cycle. And second cycle is it is going from 1 to 2 via L and returning via N, path to 1. So these are the two cycles which have been drawn here. So one by one we will apply the Clausius theorem to these cycles, right? So so when we apply the Clausius theorem to the first cycle, which I am considering state 1 to state 2 via L, and then from 2 to 1 via M. So I am applying the Clausius theorem, this simple equation, right, for a reversible cycle via 1 L 2 and M1. So I can write 1 dq by t for this path and another is for this path. This should be equal to 0. So I will write 1 to 2 via L dq by t plus 2 to 1 m dq by t should be equal to 0. This is my equation number 1. Alright. Similarly, for the cycle 1L and 2, again I can apply the same thing, right? In same equation. So cycle is 1L 2 N1. So this same equation I can write 1 to 2L dq by t plus 2 to 1 N dq by t is equal to 0. So I can write second equation. So if we compare these two equation, right? These two equation. Look at one common term is there, so I can subtract equation number 2 from equation number 1 and I can write a simple equation. So if I do that, I can write 1 to 2 m dq by t is equal to 1 to 2 n dq by t, and we have assumed these are all reversible cycle, and for reversible cycle as per the Clausius theorem dq by t is equal to the change in entropy. So if we put ds for m and ds for m is exactly equal to they are equal. If you look at these two terms, exactly they are equal, right? dq by t between 1 and 2 m and between 2 to n are equal. So we can say dq by t is a function of initial and final state of a system. It is independent of the path. Basically, if you look at quantities are same, so this is a function of initial and final state of system. It independent of the path of the process. Hence this term is represents a property of system, and this is nothing but entropy. So that's why entropy is a property of system. It is independent of the path of process. So entropy and irreversibility, let we see the case when it is a irreversible process and is a reversible process. Though we assume like it is 1 to 2 via path L, this is a reversible process and this is irreversible process, and I already mentioned irreversible process cannot be represented over the property diagram. If you want to present that, it will be presented by a dotted line. So this is a dashed line which has been drawn from 2 to 1 via M. This path is irreversible path and this is a reversible path. So if I want to write the entropy right for these paths basically, so I can write change in entropy, that is ds via path 1 to 2L ds reversible. This R represent reversible, this path is reversible, and 2 to 1 path is irreversible. So I can write 1 to 2 via L ds reversible plus 2 to 1 via M ds irreversible is equal to 0. This is my equation number 1. But for reversible process, we already know ds reversible is equal to dq by t, and dq by t can be kept over here. So this already we know. So 1 to 2 L ds reversible is equal to 1 to 2 L dq by t reversible. So if I substitute this value here, right, I can write in this way. All right. Now, since again equation number 1, that if you look at this, whatever we have applied here, this complete thing, right, starting from 1 to 2 and 2 to 1, this complete is producing a means a combining effect is like an irreversible cycle. This is an irreversible cycle. So as per the Clausius theorem, for irreversible cycle, cyclic integration of dq by t should be greater than 0. So if we are going to put that, I can write the equation like 1 to 2 dq by t plus 2 to 1 dq by t should be greater than 0. So this is irreversible, right? So as per the Clausius equality, right, I can write dq by t 1 to 2 L dq by t reversible plus 2 to 1 dq by t irreversible should be less than 0. This is equation number 4. So now subtracting this equation, right, from this equation, if we do so, equation number 4 from equation number 3, if you subtract, right, you can get change in entropy for irreversible is greater than dq by t, right, basically. So this is equation which we are getting after subtracting equation number 4 from equation number 3, because one common term is there and only this term and this term will be there. So I can get ds entropy change of irreversible process is greater than this one. So for infinite change, I can write, we can remove this integration, right? I can write dsi is greater than dq by t, or in general we can say ds is greater than equal to dq by t. So this is a general statement of change in entropy. This will be exactly equal to dq by t in the case of reversible process. If it is an irreversible process, then change in entropy will be greater than dq by t. So is that clear? Clausius theorem basically we have used here. As per the Clausius theorem, cyclic integration of dq by t should be less than equal to 0. Less than equal to 0. It will be exactly equal to 0 for reversible process, is less than equal to less than 0 for the irreversible process. Cyclic integration of dq by t is less than equal to 0. That's what we have used Clausius inequality earlier. So as per that, it cannot be greater than 0, right? That feasibility will vanish if it is going to be greater than 0. Now come to the isolated system. Isolated system was defined, it does not interact with the surrounding either via work transfer or heat transfer. So in isolated system, your dq is 0. So if dq is going to be 0, then what will happen to entropy? Entropy change will be 0, right? So in general, we can say the isolated system, right, change in entropy will be greater than equal to 0, right? This is general statement. So we can say the entropy of isolated system will keep on increasing. It remains the same only in the case when all processes are reversible. When processes are reversible, we can exactly say entropy changes the same. Means not no net change in entropy, but process are all in universe, whatever is happening is all irreversible process. So irreversible process entropy change will be positive and it keep on increasing. So how to how to design an isolated system? Isolated system we can be designed if we put system and surrounding together in a single boundary. Then if you are standing at the boundary of that case, then that combination of system and surrounding together will be considered as universe. So nothing will come out from the universe boundary. So whatever change will happen in the system will be reflected only in the surroundings, right? And nothing will go out of the surroundings. So if we consider the case of like this one, we are enclosing system and surrounding together in a single boundary. This is a boundary, right? And this boundary is called universe. So nothing will come out of it. So whatever changes will happen in system will be reflecting only in surroundings. So whatever heat is getting transferred from here will be taken away by the surrounding, and nothing will go beyond that. So the system and surrounding put together is known as universe, right? So by including any system and surrounding within a single boundary as shown in figure is known as isolated system. So combination of system and surrounding within a single boundary is called universe. So we can write ds universe is greater than 0. So change in entropy of universe will be greater than equal to 0. So we can say the entropy of universe keep on increasing. It remains constant only in the case of reversible process. Right, that's the general statement of entropy principle. So we can say ds universe is equal to ds system plus ds surrounding, right? We can write this simple equation. So ds system may be assumed like some heat is going away from the system, so system is losing heat, so minus dq we can write, and surrounding is gaining something, so plus we can write. So ds system is basically minus dq by t, right? And the same thing is getting supplied to the surrounding. Surrounding is at temperature. So surrounding can be considered as a reservoir temperature will not change. So ds surrounding is dq by t naught, right? And dq by t is my system change in entropy, right? These are two reservoirs basically. From system some heat is going and another getting supplied to another reservoir. So minus dq by t is from system and dq by t naught is from to the surrounding. So if we add these two terms, we can get the change in entropy of universe. So if I add this, I can get this one, this term. So same results can be obtained in the case of open system. If we make the open system and or closed system, we can get the same results like change in entropy of universe should be greater than equal to 0. This statement should satisfy, right, for any feasible process, right? It cannot be less than, right? It cannot be less than. So ds universe should be greater than equal to 0, right? If it is going to be less than 0, that kind of process is not possible. Keep in mind. So since all natural processes are irreversible in phenomena, so entropy is keep on increasing continually for the universe. Now entropy change in any irreversible process, how to find out? So let's suppose we are assuming now two cycles. One cycle is reversible, completely reversible cycle, that is 1A, 2B, 1. Another we can say irreversible cycle, this combination we can consider, right? 1 to 2 via C path and returning via B. So B is common in both, right? B is common in both. So we can apply now Clausius theorem. So as per the Clausius theorem, for one cycle, that is 1A to B1, this cycle I am considering, this is completely reversible cycle. So cyclic integration of dq by t should be exactly equal to 0. So I can put 1 to 2 dq by t A plus 2 to 1 dq by t B is equal to 0. This is one equation I got. Now I will consider this irreversible cycle. For reversible cycle, cyclic integration dq by t should be less than 0. Right, so a second equation can be written this way: 1 to 2 dq by t C plus 2 to 1 dq by t by B should be less than equal to 0. If you look at these two terms, B is common, so I can subtract equation number this one from equation number 1. So subtracting equation, second equation from first, I can write dq by t of A is greater than dq by t of C, right? dq by t of C, this one thing I got. But path A is reversible basically. For reversible cycle, reversible path, we can say dq by t is exactly equal to the change in entropy, right? So since path is reversible, so I can say dq by t A is equal to dsa, and entropy doesn't depend on the path of process. Already we have proved that. So whatever change in entropy of A is there, that will be the change in entropy of C as well. C is in a reversible path. So if I substitute this value in that equation, which equation here, which I got here, so I can put ds here C. So if I substitute there, ds as C is greater than dq by t. So in generally we can say ds C is a reversible path. So change in entropy of a reversible path will be greater than dq by t. So in general we can say ds is greater than equal to dq by t, or s2 minus s1 is greater than equal to dq by t. That is the general statement. So this will be exactly equal to dq by t in the case of reversible process. It will be greater than dq by t for irreversible process. Just keep in mind this general statement of change in entropy. Now we are going to derive expression for change in entropy for a closed system. So we'll start from closed system, then we'll go for open system. So we are taking the general case of entropy. So general thermodynamic process and polytropic process, right? So let 1 kilogram of gas at a pressure of P1, volume B1, absolute temperature T1, and entropy S1 be heated such that its final pressure, volume, absolute temperature, and entropy are P2, V2, T2, and S2 respectively. Then by the law of conservation of energy, that is first law of thermodynamics, what it says, dq is equal to du plus dw. Don't make the mistake, this will be dou q is equal to du plus dou w, because I cannot write exact differential for heat and work. So now we already know dq is equal to C, du is cv dt, and work is in closed system is only displacement work, that is called pdv, right? So I can write this. If I divide the entire equation by absolute temperature T, I can write in this way: dq by T is equal to cv dt by T plus pdv by T. Now I will use the ideal gas equation of state, right, to put the value of P here. But this term basically dq by T is nothing but change in entropy as per the Clausius theorem. So dq by t is ds, and this p, that is pv is equal to rt, so I can write p by t is equal to r divided by v, where r is the constant, that is called characteristic gas constant, v is called specific volume. If I substitute these values in this equation, right, I can write in this way: ds is equal to cb dt by t plus r dv by v. If I integrate now this between 2 points, right, point 1 and 2, I can integrate in this way, right, ds s1 to s2, and this dt by t, t1 to t2, and r b1 to b2, dv by b. So if I integrate this, I can get one relation for change in entropy. So change in entropy, this specific entropy I am saying, because I am writing small letter, so specific entropy unit will be joule per kilogram Kelvin. So S2 minus S1 is equal to Cv ln of T2 by T1 plus R ln of V2 by V1. So I got this general expression for change in entropy. So this can be applied to any kind of process. So now we got a relationship for T2 and B2. Let me relate now T2 with P2, then we'll relate P2 with V2. So now I am doing some more adjustment. So I will be using same ideal gas equation of state. So P1 V1 by T1 is equal to P2 V2 by T2. So in place of this T2 by T1, I am going to write only P2 and B2, so I can relate this complete thing in terms of pressure ratio and volume ratio. So T2 by T1 is equal to P2 by P1 into V2 by V1. If I substitute this here in first equation, right, here in this term, right, so if I do so, right, I can substitute in this way. Now I can separate these two, right. So Cv ln of P2 by P1 plus Cv ln of B2 by V1 can be written. So if I rearrange the terms, I can write in this way. Now I combine these two terms together, right, Cv plus R, right, I can write. So the Cv plus R is nothing but Cp, right. So one is term is the Cv ln of Pt by P1 plus Cp ln of V2 by V1. So this is Cp, right. So Cp minus Cb is equal to R. So Cp is equal to Cb plus R. So this is Cb plus R ln of V2 by V1. So this is equation number 3. Right. So this is related in terms of pressure and volume. Now next expression I am going to relate within temperature and volume, or temperature and pressure. So let's see relation between pressure and temperature. So again I will use same equation of state. So P1 V1 by T1 is equal to P2 V2 by T2. So V2 by V1 became now P1 T2. Why I am doing? Because I want to convert this equation in terms of pressure and temperature only. So in place of this V2 by V1, I substitute this P1 by P2 into T2 by T1. Just you put it here. If you do so, you can get this equation. You can again separate the term, and then you add this and this term together, right. If you add this term, this will become Cp, right. So if you do so, I can write Cp ln of T2 by T1 minus R ln of P2 by P1. So I can get this general statement of change in entropy. So I got three relationship: one in terms of temperature and pressure, another I got in pressure and volume, and I got another relation with pressure and volume and temperature. So first equation is this, second equation is this, right, this can be used, or third equation is this can be used. So these three equations can be used to find out the change in entropy to any kind of process. We are having 5 types of processes, right. So this can be used in any kind of processes based on the assumptions. So I will take only one example, right, for today's lecture. With that I am closing. So heating a gas as constant volume. So this is the constant volume process, can be represented on TS diagram in such a way that this is the constant volume process where temperature is increasing from T1 to T2, right. Area under the curve over the Ts represent the heat transfer. So this is the heat transfer involved. So it's a constant volume process. That means V2 and V1 both are same. So V2 is V1 is almost same. So I will get the expression very simple, right. That is Cv ln of T2 by T1. If I use the temperature ratio and volume ratio relationship from the general entropy change relation. So Q is Cv dt. We can write dq is equal to Cv dt. If I differentiate, I can write ds is equal to Cv dt by t. If I integrate, I can get change in specific entropy is equal to Cv ln of T2 by T1. This is the one way. Or if you know the what is say first formula that we use, you can utilize this formula to find out the change in entropy for a constant volume process. If you put B2 is equal to B1, this term will vanish. So I can get change in specific entropy is equal to Cv ln of T2 by T1. Or you can derive from the basic fundamental like it has been derived. dq is equal to Cv dt, so dq by t is equal to Cv dt by t, so ds is equal to Cv dt by t. Like that you can derive. So with this, basically I am going to close the discussion today. In next lecture, right, we will see the application in rest of the processes of this entropy. Then we will proceed to the open system. So if you are having any doubt, right, feel free to contact me at any time. All right, already I shared my WhatsApp number with you. So thank for your patience today for listening this lecture. Have a nice day. A good day.